Hello everyone. In today's lecture, we will be looking at indeterminate forms and LHopital's rule. As usual, we talk about the topics we will cover today, and then we look at the material. So the topics we'll be covering is indeterminate forms, recognize the limits which produce them, and then apply LHopital's rule to evaluate those limits. So let's start with an example of an indeterminate form. Now, in earlier chapters, we have encountered indeterminate forms of the type 0 by 0 and infinity by infinity. Now, these forms do not guarantee that a limit will exist, nor do they indicate what a limit is. And when we encountered one of these forms, we rewrote those expressions by using various algebraic techniques. So let's go ahead and look at some of these examples. So the first example is limit as x approaches 1 of x cubed minus 1 over x minus 1. Now when I substitute 1 over here, what do I get? A 0 by 0 form. So we have learned the technique because this is a cubic function and it's an x cubed minus 1. We can actually factorize it and we can write the top as x minus 1 times x squared plus x plus 1. And when we do so what happens is this expression of x minus 1 in the numerator and denominator cancel. And we get limit as x approaches 1 of x squared plus x plus 1. And when we substitute 1 here, it's like direct substitution here, we get the answer to be 3. Now, we will also look at the example for infinity of infinity. So if limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1, clearly when we substitute, what do we get? Infinity over infinity. Now, this one is not going to give an answer. And also, we cannot easily factorize this one. But there's a technique we have learned. And that is, if you have a rational function with a polynomial over a polynomial, and you look at the denominator, the highest power here is a 2. So what you do is you divide the numerator by the highest power here, 1 over x squared, multiply the numerator and denominator by 1 over x squared. So what are we getting? So what we get is 3 minus 1 over x squared over 2 plus 1 over x squared. And we know that the limit as x tends to infinity of 1 over x squared is 0. So our answer is 3 over 2. Now, we were having nice little, polynomials. But we can also apply these techniques when we have transcendental functions. So let's look at those transcendental functions. Now, here's an example. If we have a limit as x approaches 0 of e to the power 2x minus 1 divided by e to the power x minus 1. So we have an exponential function here. Now, if I substitute x over 0, what do I get? E to the power 0, which is 1 minus 1, which is a 0, divided by, again, e to the power 0 is 1, 1 minus 1 is 0. So clearly, it's an indeterminate form of 0 by 0. So we see what other algebraic technique can we do so that we can find the limit value, if possible. Now let's look at the numerator. The numerator is e to the power 2x minus 1. If you remember, it's a difference of squares. E to the power x minus 1 times e to the power x plus 1. When you multiply, you get e to the power 2x minus 1. Now with that factorization, we can easily cancel out e to the power x minus 1 over e to the power x minus 1. So that was the problem which was happening. So when we removed this common term in the numerator and denominator, we are left with e to the power x plus 1. So when we apply the limit, the answer is C, straightforward 2. Okay, there are scenarios where not all indeterminate forms can be evaluated by these nice little algebraic techniques. So let's look at an example of that. And most of the time, these scenarios happen when we have some transcendental functions like logarithms, you have exponentials. So those kind of functions give us an idea. Okay, so let's look at an example here. Limit as x approaches 0 of e to the power 2x minus 1 over x. So when I substitute 0 in this expression, what do I get? A 0 by 0. So even if I do the algebraic manipulation as I did in the previous example, here, I will not be able to solve it. So let's say if we try something else, okay? So let's rewrite this expression. I can rewrite this as, pull the x apart in both the terms on the top. We get this e to the power 2x over x minus 1 over x. So it just produces another form. It's 1 over 0 minus 1 over 0, which is infinity minus infinity. Still not getting us an answer. But let's see if we have some other techniques by which we can do so. And yes, we have. If we apply, just simply, graph this function, e to the power 2x minus 1 over x. And as x approaches 0, notice clearly at this it is not defined. But when you look at the value close to the x as x approaches 0, notice the function is approaching 2. Okay, this is clear from our graphical solution. Okay, so we see the limit exists, but it is coming to 2, but we're unable to do it using our normal algebraic techniques. Just to make it doubly sure, let's do a table of these values to see what happens when x is coming closer to 0. So notice if I'm taking values minus 1, minus 0.1, minus 0.01, minus 0.001 close to 0, it's not defined at 0, clearly this expression. But as I'm coming closer to 0 from the left-hand side, I see the values are approaching 2. Similarly, when I'm coming from the right-hand side, the values I also notice is approaching 2. So we know that the limit is 2 by our graphical technique and our numerical techniques here. So we would like to see how we can find it with an algebraic technique. And for that, the answer is the LHopital's rule. Now, what this theorem is saying is that under certain conditions, important, remember, under certain conditions, the limit of the quotient of functions is determined by the limit of the derivatives of those functions. Okay, that's in a very simple way of saying it. So let's look at those formal definition theorem here. Now, if f and g are two functions which are differentiable on an open interval a and b, containing c except possibly at c itself. And we're going to assume that the g prime of x, that is the derivative of gx, is not 0 for all x in this interval a to b, except possibly at c itself. And if the limit of the function f over g as x approaches c produces this indeterminate form, the 0 by 0, then the limit as x approaches c of f over g is the same as the limit of x approaches c, f prime over gx, provided, very important, provided the limit on the right-hand side of this equal sign exists or is infinite. Now, this result also applies when the limit of the function as x approaches c can be either of these indeterminates, infinite over infinite, negative infinite over infinite, infinite over negative infinity, or negative infinity over negative infinity. Not only is going to be applied to x approaches c, but it can also be applied to our one-sided limits. That is, limit as x approaches say c plus over f over g is the same as limit as x approaches c plus, that is, we are approaching the limit from the right-hand side, f prime over g prime. And once again, provided the limit on the right-hand side exists or is infinite. Now, another form of the LHopital's rule states that if the limit of f over g as x approaches infinity or minus infinity will also produce the form 0 over 0 or infinity over infinity. And the limit of this f over g as x approaches infinity is the same as the limit as x approaches infinity over f prime over g prime. So notice the fact is that the f over g should have either of these two indeterminate forms, and we can apply our LHopital's rule provided the limit on the right exists. So this is our theory. Let's go ahead and do some examples. We all know that the limit as x approaches 0 sine x over x, we have done that very early on, is 1. We all know that, right? And this time, we're going to apply the LHopital's rule to it. So let's start. So we have limit as x approaches 0 of sine x over x. Now clearly, when you substitute x, sine of 0 is 0 and x is 0. So 0 by 0. Now we can apply the LHopital's rule. That means we can take the differential. Remember, the differential is existing here. So it's 1 over cosine x. And when we substitute x to be 0, what do we get? We get cosine 0. And we all know cosine 0 is 1. So we have proved this limit value using LHopital's rule because, this was an indeterminate form. Okay, so here, make sure, guys, when you're doing these problems, write down using LHopital's rule. Okay, let's look at the next problem. Now, this one is limit x approaches infinity e to the power x over x squared. Now, let's substitute here. E to the power infinity would be infinity over infinity squared, again infinity. So it's an infinity over infinity. And we can, and the f primes and g primes are existing. So let's go ahead and apply the LHopital's rule. So using the LHopital's rule, we get limit x tending to infinity over e to the power x over 2x. Now once again, we notice, what is this expression? We substitute infinity, what do we get? We again get infinity over infinity. So we can still apply LHopital's rule. And what are we getting now? Limit x tends to infinity e to the power x over 2. Now in this scenario, once we substitute infinity e to the power infinity over 2, our final answer is infinity. Okay, so those are very simple ones. Let's pick up some rational functions with square roots and stuff. Okay, let's look at this example. Limit as x approaches 0 of square root of 1 plus x minus 1 minus x over 2 over x squared. So the first go, let's substitute 0 and see what we get. We substitute 0, we get 1 minus 0 over 0. So it's a 0 by 0. So the next step is, okay, as it's a 0 by 0, we can apply LHopital's rule. So you can write equal to, you can write LH over here also if you want, or you can write LHopital's rule here if you want. It doesn't matter. But if you write LH, it's a common knowledge, you'll know what you're doing. So now we're going to take the differential. So the differential of -1 is 0. Differential of negative x over 2 is -½ Differential of x squared is 2x in the denominator. So let's look at the differential of 1 plus x to the power ½ This differential is half 1 plus x minus ½ which is the same as half, and then you can write 1 plus x. That's what I've written here. Now, when once again, we substitute 0 here, what do we get? 1 over 2 minus 1 over 2, again we get what? Again in the 0 by 0 form. So that means once again we apply the LHopital's rule. LHopital's rule. Okay, so differential of 2x is 2. Differential of -½ is 0. And what do we get? Now let's do the integral of 1/2. So now let's do this differential of this now. Suppose this is y. So y prime is what? Half here. Now this one, or if you look at this one, we get -½ 1 plus x minus 3/2. So what do we get? -1/4, 1 plus x to the power -3/2 over 2. Now let's substitute the 0 here and see what we get. So this one, when you get 0, 1 to the power -3/2, again is a 1. And we have now -1/4 over 2. And the final answer, sorry, that should not be there, is -1/8. Okay. Let's look at another example. Limit as x tends to infinity, natural log of x over 2 square root x. Now when you substitute infinity in place of x, what do we get? Infinity over infinity. So once again, we're going to do the LHopital's rule. And differential of natural log of x is 1 over x. And differential of 2 square root x. So it's 2x to the power ½ which is 2 over 2 x minus ½ which is 2 over 2 square root x. So this cancels out 2 over 2. And what do we see? This is 1 over x over 1 over square root x. We can write this as 1 over x times, flip the denominator fraction, square root x over 1. And what we see is limit as x tends to infinity, square root x over x. Now we can still do a little bit algebra here. This is x to the power ½ over x, or 1 over x 1 minus ½ which is 1 over x to the power ½ So it's all algebra here, guys. So what do we notice? The limit as x tends to infinity of this nice little expression is very simple, 1 over square root x. Okay? And when you substitute x to infinity here, 1 over infinity is 0. Okay, guys. Once we have learned some new techniques, what do? We practice. So here is what I would like you guys to practice. And in the next session, I will be talking about other kind of indeterminate forms. Thank you.